Previously, in information retrieval, a user typed a query in the search box of a website. That query is called Q. A little elf in Antarctica picked a document at random in the entire library of documents, generated a model out of that document by writing a Python script in an hour to build the conditional probability tables, used that model, generated the document, and then the incredible happened. The elf just regenerated query Q. What are the odds of that? Incredible, right? And so we asked the question, what document is the most likely to have been picked and to have generated Q? So it's a conditional thing, conditioned on the fact that you've been informed that the document that was generated was Q. What document has the highest likelihood of having generated Q? Do you see that this gives us an information retrieval system? Because if we are able to compute the probabilities that it was a specific document D and we order them by descending probability, then we have just built a system, right? And we just return the documents that have the highest probability. And so this is called the query likelihood model when we build a system like this. And concretely, that was my puzzle before the break. When you have a conditional probability that is difficult to compute, you use the magical Bayes theorem to just swap it. So in that case, we want to know the probability that it was document small d, the one we want to rank, right? We are going to compute that for every document small d and then order by that. But I pick, let's say, a specific document, conditioned on the query Q, but I have no idea how to compute that. But with the Bayes formula, I just swap them. It's a probability of generating query Q given documents D, multiplied by the probability that it was document D, divided by the probability that it was query Q, right? Do you agree with that? That is just the Bayes theorem. But now the incredible happens because this is a constant. This doesn't depend on the document, right? So I can just get rid of that. That's not going to change the ordering. This, we can just consider it's uniform, right? That a priori, any document is just as likely as any other, was picked randomly. So this, we can just consider it 1 over the number of documents, which leaves us with this. But this is great because that we know how to compute. I spent an hour explaining this, right? With this multinomial distribution and all the chain probabilities to generate. So that I know exactly how to compute. This is exactly what we have done in this lecture. And here is the formula. If you remember, that's my big, scary multinomial formula. So I took multinomial, the unigram model as an example. I could, of course, use bigram, trigram, and so on. But I just wanted to stick to the unigram model. But you notice a bit of a difference with before. There are some letters that have changed. And the letters that have changed are here. It's Q now. In the previous formula, it was D, but that's only because I used to call it D what I was generating. Now I'm looking at the probability of generating Q, right? So of course I need to look at Q in order to have the probabilities. So Q, imagine that it's a bag of cats, and then I'm looking at all the possible colors in there, so as a bag of cats, and then I'm multiplying the probability of every cat to the power of a specific color to the power of the number of cats with that color. So that's my formula of before, right? But it depends on Q because that's the query that I want to compute. What's the probability of generating the query, right? So this is why I have Q in there. Where does the document intervene in that formula? Well, that gives me PT, the probability of specifically generating a term comes from the term frequency analysis of document D, because I use document D to generate my model. Who is with me? Right, everybody? So I use document D, I build the probability table out of documents D, and then I look at Q, and then I compute the probability of generating Q based on the probabilities that I inferred from documents D. And then, of course, P stop, and again, that's LQ in here because we want to make sure that we generate Q. So it has to be exactly the length of Q. Now, PT, as I said, was generating generated out of document D. And in fact, I just divided the term frequency of the term divided by the length of document D, right? That's the easiest way to use statistics to compute a probability out of a document. So careful, this is why I have D in here, because I use document D to build my probability weights, but I'm computing the probability of generating document Q. We still with me? Right? It's master's level now, right? So it's pushing a bit further. So this is basically the big formula that I want to evaluate for every document. So I'm going to compute that 1 billion times for every small d, right? Q, that's whatever the user entered in the search box, that doesn't change. But D, I'm computing that for every document, and then I'm going to rank the documents based on the value of that. The documents that give me the highest value here are going to be ranked first, and then decreasing. Now, we are going to do a little bit the same sort of things we've done with probabilistic retrieval. I'm going to cook a little bit here and try to turn it into something that looks a bit like evidence accumulation, and then we'll see what comes out of that. So first, you remember that here I have a big product, but when I accumulate evidence, I like to have sums, right? How do I transform a product into a sum? I take the log. So we are going to take the log of that. And that's what we get. And now, just like I did for probabilities, I'm going to look for what is constant and what is not constant, right? Because I might be able to get rid of some of the things in there, right? And so if you look in here, what depends on D and what doesn't? That doesn't depend on D, right? That's just a constant. We don't care for the sorting. That is also a constant. So we don't care. Here, I need to be careful. There is D, so this is not constant. That's going to change with the document. This is constant. There is no D in here, no D in here, no D in here. This is all constant. So the only thing that's actually not constant is this, right? So I'm going to put all the rest in C. That is a constant that doesn't change with the document, plus my sum, because now I have a sum of this right here. And now, this is where it starts to look really, really cool, because now you're probably starting to connect a few dots with what we've done before. This is a sum of products of which the first factor depends on the query, and the second factor depends on the documents. This is a scalar product. What do we have in the scalar product? We have a term frequency for the query. We've seen that before, right? In the vector space model, we had a term frequency in the scalar product. And here I kind of have a term frequency too, but I took the log. But that also we've seen before. Remember, in the smart menu, I can select something different. I don't have to have the term frequency. I can also have the log of that. I have all kinds of variations. So basically, what I see here is basically just a scalar product of some vectors that are based on term frequencies. We have just reinvented or rediscovered the vector space model with the justification now that we use term frequencies in the vector. This, we can put it separately. We can maybe assume all documents have the same length or whatever, or get renormalized, but this is really the focus right here. Who sees that it's a scalar product? Right? This is exactly my evidence accumulation, and that I can compute in exactly the way that we've seen before. So now, if I get back to what we've done 2 weeks ago, we have discovered that probabilistic information retrieval, after doing a bit of cooking with the Bayesian rule and probabilities of relevance, and we got the IDF out of the hat. And now we've done the same thing with language models, and we've got the TFs out of the hat, right? So it's all connected, just gives a justification for the TF IDFs, right? And so this is why the vector space model, in a way, can be considered as a kind of system that is based on language models, the justification for the term frequencies being the idea that the term frequencies give you the probabilities of generating a specific document. That is the high-level idea, right? So, yeah, what a delight to see that we land back on our feet and find exactly the factors that we've had before. So I feel just like that cat over here, seeing such mathematical perfection. All right, so probabilistic models, IDF, language models, term frequency, and we get the TF-IDFs that we had in the vector space model. Then there's a few variations, but again, that's part of the smart menu that we've seen before, this idea of smoothing. So imagine that you compute your TF-IDFs and then infer the probabilities for the documents. Then you're going to run into the issue that I mentioned before, is that a document might be too small to generate anything. For example, you might have a query information retrieval, and then you might have documents that do not even contain information of retrieval, right? And if you build a model based on the document that does not contain information of retrieval, then what probability do you get for these terms? 0, right? Term frequency is 0, the probability becomes 0, and so the probability of generating the query is 0, right? Just because the document was too small and a lot of probabilities are 0. And so when we have a sample that is too small and would give us probabilities that are 0, we can smooth it a little bit. And you remember, we just add some constant a little bit everywhere. And this is what some people do. So they basically take this term frequency evaluation, but they smooth it a little bit, not with a constant. You could do it with a constant, but another idea is to smooth it with the collection frequency. Right? So you look at the collection frequency in the entire collection, and then you take some, it's like cooking, right? So you cook something with a bit of the term frequency and a bit of the collection frequency. And that takes care of the smoothing, right? Transforms it into something a bit more smooth that's going to not have too many zeros in the probabilities. Who is with me? Right? So we just tweak it a little bit to nudge it in the direction of the collection frequency. That is the query likelihood model, where we generate the models from documents. There's other approaches that I will not go into, but just mention that some people do it the other way around. They generate a model based on the query, and then compute the probability of generating each document based on the query. As you can imagine, this one is more tricky because the query is very small. Right? The query might just have a few words, so how can you generate a model out of a query? But again, if you smooth with the collection frequency, maybe you can manage to get something out of this, right? But this other approach, which I'm not getting into, is called the document likelihood model, right? Then you don't need the Bayesian formula anymore because you directly compute the probability of generating D with this scary formula that I've shown you with all the scary factorials and products and so on. And finally, there is a third approach where you generate both models. You generate a model for every document, you generate a model for every query, and then you compare the models. You look at the distance between the models. The documents whose model is closest to the model based on the query is ranked higher, right? How do you compute distances? Quick example, imagine that what characterizes a model is the probability weights, right? In the unigram case, that would be the probability weights. That basically comes down to computing the distance between two probability distribution, right? And so there are formulas, magic formulas, that give you the distance between probability distribution. An example of that is that you compute the absolute difference between every possible value, and then you sum all of that, and then you divide by 2. That gives you an example of distance. It's going to be 0 if all the probabilities are equal, and it's going to be 1 if they are as far away as they can be. So basically, it would be the case that the supports of the two probability distributions are completely disjoint. But basically, there are ways. So you can compute the distance between two probability distributions, and then you would get yet another way to build information retrieval engines. I press, and there's no more slides because you have made it through the entire material of the semester. This is it. So congratulations on that, especially because the probabilistic and language models was already more advanced. than the rest. But at least now we know why TF and we know why IDF. So I'm going to stop for a few questions, if you have any questions, and then I will ask you questions. We'll just use a bit of the time left to rehearse a bit. Do you have any questions? Anything? Well, then I repeat a question that was asked during the break. Then you can still ask a question after that, but just because somebody asked. And it's important that you understand this. In this formula right here, what's important is to understand that the product here is just on this. This is what we multiply. This here on the right is separate, right? That is not in the that is not a factor of the product. So you have to cut it in here, and the product is just this. Right. Any questions in the meantime? Who understood what I've been telling you today? Okay, many raised hands. Awesome. So great. So I will ask you questions, then I'll go to the clicker and I see. So maybe some easy ones. Then I'll give you more of a challenge. So let me prepare it. Okay, let me start with an easy one. So what fundamental rules of probabilities did we use and apply to information retrieval? Bayes rule, the partition rule, the pigeonhole principle, or the addition law of probability? And indeed, so the Bayes rule, this is the rule that you use when you're completely stuck and you need to compute conditional probabilities and have no idea how to do it. There's a good chance that the Bayes theorem is going to help you. Okay. Let's have another one. Okay, let's go to this one because it's actually fun. Then you can think a little bit. So I'm giving you 3 boxes. In the first block, there are 2 Toblerone. In the second box, there is a Toblerone and a Luxembourgerly. In box C, there are 2 Luxembourgerly. You pick a box at random, one of the 3, and then you go home. And at home, you pick a candy without looking in the box. You just pick a candy randomly in that box, and you notice it's a Luxembourgerly. And the question is, what do you think is going to be, what the probability that the other one is also a Luxembourgerly? You probably know what theorem you have to use, right? But the difficulty here is the modeling, because you of course, will need to use the Bayes theorem, but you need to know with what random variables. This is the difficulty in here. What random variables do you use? I already have 10 answers. Wow, that was so fast. I would never have solved that so fast. Did you guess or estimate? Who is actually calculating, writing down the Bayes? Ah, awesome, perfect. That is called the Bertrand paradox, this problem right here. Let me look at your answers. So we have a majority 1/2. So maybe Luxembourg-early, maybe Toblerone. And we have 9 people who said 2/3. So basically it's a higher likelihood that it's a Luxembourg-early than of being a Toblerone. Will I give the solution? I see no more answers. The solution is 2/3. But of course, I have an animation for you to show you why and how we come to 2/3. So these are my 3 boxes. So you have the first box with 2 Toblerone, the second one with 1 of each, the third one with the Luxembourg early. And at the bottom, you see my 2 random variables that I use in the base formula. So I have a first random variable that contains the box A, B, or C, right? So that's a random variable that can take one of 3 values. So then I can write the probability that the box is A, or the box is B, or the box is C. The other probability, the other random variable that I have is whether the candy that I have, that I took out of the box, either Toblerone or Luxembourg early, right? So this one is a binary. It's either Toblerone or Luxembourg early. And once you have these 2 random variables, you agree that what I'm looking for is the probability that we are in box C, given that the candy is a Luxembourg early, right? It's an equivalent way of saying that the other candy is also Luxembourg early, because only box C would give me a Luxembourg early as the other one. Do you agree with that? Right? So I need to compute the probability that we have box C conditioned on the candy being a Luxembourg early. But that I don't know how to compute. So I use the base formula and I swap them. Now I have the probability of having a candy condition on the box, should be easier, and the probability of the box, probability of the candy. So what is the probability of getting box C? 1/3, exactly, because I pick the box as random, right? So 1/3. What is the probability of picking a Luxembourg early in box C? That is 1, absolutely, because both of them are Luxembourg early, so that's 1. And what is the probability without any condition, right, of picking a Luxembourg early as a candy? 1/2, exactly, because I have 3 Luxembourg early and 6 candies in total, so it's 1/2, right? Without conditioning on any box and anything. That, of course, is only true because the box have the same number of candies in each, right? If that hadn't been the case, that we could have said that. All right. So I just replace 1/3, 1, 1/2, and I get 2/3 out of that. Right? And you can even see it visually. When you apply the condition that it's a Luxembourg early, you're in one of these 3 cases, and in 2/3 of the cases, you are in the 3rd box, right? That's just the visual that corresponds to the application of the Bayes rule. All right, so that is the Bertrand paradox. And it's 2/3 and not 1/2, as one might have thought a priori. All right. Let me give you another one. Oh, no. So, let me see. That's just to take a bit of a break because I have a more complex one after that. You remember how we decrease the number of false positives with phrase queries, right? If we use a byword index, we might get false positives, so results that actually do not match the query. Do you remember how we decrease the number of false positives? Do you need to increase the tuple size, reduce the tuple size, post filter, but not eliminating them completely? Ah, okay. The correct answer was actually this one. You increase the size of the window, right? The number of tuples, that's going to reduce the false positives. It's not incorrect that you can eliminate them by post-filtering the results. That's not the problematic part. It's the fact that then there are no more false, I get it, false negatives. No, that there are no more false positives. That's of course what I meant, right? So if you post-filter, the false positives are completely gone, right? Okay. That's the typo I made that might have led you to answer this one, I guess. There may still be some false negatives, but I think that would also be incorrect, right? There would also not be false negatives in the results. Okay. So this is the reason why this is the correct answer. Smaller tuples of words would make it even worse, right? Because then you would have even more false positives in the results. Another one, why do you think we use inexact top K retrieval? You remember inexact top K retrieval is when we want to return the top 10. Normally, we would need to compute the score of every document, but instead of computing the score of every document, we only compute the score of some documents that we pre-select. And so the question is, why does inexact top K retrieval make sense? So is it because precision is irrelevant to ranked retrieval and only the relevance of documents is relevant, which is why they are ranked? Or is it because it leads to increased precision and increased relevance at the cost of being slower? Or is it because using cosine computations on vector representations as a linearity measure is already an approximation of reality, so going inexact does not hurt the results so much? Or does it not always make sense? And actually, inexact top K retrieval does not make sense if K is 5, 8, or 13, but it makes especially a lot of sense if K is equal to 10. And the majority is correct. That's indeed the case. So this is why you really should not forget that when we come up with all these formulas, you know, be it the probabilities, the language models, or the cosine computations, the scalar products, you should never forget that all of that is an abstraction and an approximation of reality. It's just a trick to implement a system that delivers results, but it's not exact, right? The scalar product does not give you an absolute truth on the relevance of the documents. And if you have that in mind, then you realize it's already an approximation. And so inexact top K just approximates the approximation. So that's the idea. Let me give you then the one that I had in mind. Which one is it? I think that's the one. Yes. So now it's about what we've done today. Except instead of the cats, I'm using words now. So the query is foo bar foo. This is what somebody typed in the Google box. And you have documents in here that all have a length of 4 to keep it simple. So I'm asking which ones of the following documents would be returned on top as the first results of the query following the language model approach that we have with unigrams, right? So we ignore the past. With bag of word semantics, so it means we grouped everything into the bag of word model, and no smoothing, also to keep it simple. So which one is returned on top, or if there's some with the same score, maybe several, but that's the one. So the query is foo bar foo, and these are all the documents. Normally, doing it on a concrete example should also activate the brain, to make sense of the formulas and understand the mechanism. So remember that in the query likelihood model, the one that we saw, we generate a model for every document, right? So every one of these documents will give you a table of probabilities. These probabilities are computed based on the term frequencies in each document, renormalized, of course, by the length in order for them to sum up to 1, right? As an example, bar, 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 that would give you a lookup table with a probability of 1 for bar and 0 for foo, because there's no smoothing. And the last one, foo, 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 would be, that would be probability of 1 for foo and 0 for bar. Foo bar would be 1/2, 1/2, right? So you have to remember the formula for the generating specific query, foo bar foo in that case, and you need to compute the probability for each one of these models of generating foo bar foo, and the highest the probability, the higher the ranking of the documents. Let me look at the results. Ah, you like this one. And it is the correct answer. Indeed, foo, foo, bar, foo gives probabilities of 3/4, 1/4, right? So let me show you on a slide. Make sure you understand. So remember all the components of the formula, right? You have the multinomial coefficient that you multiply with. And then you have the products of the probabilities to the power of the numbers of colors. And then you have p stop 1 minus p stop. But you remember that whenever we have to compute so many formulas, we need to find out what is constant and that we can throw away, right? Because we should not bother computing constants. Who sees that the multinomial factor, this factorial of the total divided by the product of the factorials, is a constant based on the documents? Why is it a constant? Do you see that we are computing the probability of generating Q, the query? So it means that the multinomial that we are going to compute is based on foo bar foo, right? That's 3 factorial divided by 2 factorial, 1 factorial, because I have 2 times foo and 1 times bar. That only depends on the query. It doesn't change. If I take a different document, I still have the same multinomial factor, because that's based on the output of the model. So that we get rid of. We don't need to bother with the multinomial coefficient. One less thing to worry about. Who agrees that 1 minus p stop to the power of 4 and p stop is also a constant? Right? That's because all the documents I gave you have a length of 4. That's why. So we can get rid of that as a constant. So all we have left are the products of the probabilities of the terms to the exponent of the number of times they appear in the query. So it means that I just need to compute that. So I'm going to look at each document and I'm putting my probability lookup table, right? Do you see probability 3/4, 1/4, 3/4, 1/4, 1/2, 1/2 for foo bar, foo bar bar, 1/2, 1/2, foo bar foo, 1/4 for bar and 3/4 for foo, and so on. Does everybody agree with these probabilities, right? So in that case, of course, I put them horizontally. The way I displayed them on the slides was vertical. There was 1 term per row, but here there's only 2 terms. So I put them on a row fashion, right, instead of a column fashion, just so that I can display my 7 models on top of each other. All right. And then I need to compute the products of these probabilities, but I need to use the exponents as they appear in the query, right? So it means that since in the query foo appears twice, I need to take the square of p foo and then multiply by p bar. Who agrees? Right? Who agrees? Yes, based on the query. And so now if you compute that, probability of p foo squared times p bar, the first line is 0. The second line, it's always time divided by 64, right, in any case. So 1 times 1 times 3 gives 3. 1 times 1 times 3 is 3. 2 times 2 times 2 gives 8. 2 times 2 times 2 gives 8. 3 times 3, because that's the one we operating. What is the formula for operating? No. Okay. Okay, I cannot operate. Anyway, 3 quarters, so 3 squared, that's 9 times 1, that's 9. So we have 9 divided by 64, and then 1 times 1 times 0, so we have a probability of 0. And now you see the maximum is 9 over 64, right? So this is why the document foo bar foo is the one that comes first, because this is the one that generates the query with the highest probability. Of course, it's not a huge probability, right? It's a low number, but we are comparing them across documents and taking the number that appears the longest. All right? Who understands? Right? Okay. Awesome. So this is the language model. And as you can see, in the end, we're actually looking at the term frequencies of the documents that influence everything. Okay. All right. So that's actually pretty much it. So going to maybe if I come back here. Okay, no, apparently I can no longer appear, so people on Zoom cannot see me anymore. But anyway, thank you very much for attending today. You can get to have an early lunch. Please come next week. Everybody who can come, if you come on Zoom, try to come in presence because we're going to have this big quiz. We're going to have the prizes, chocolate, and so on. So if you are in the lecture hall and you win, then you can actually get the chocolate. And also because it's nice to celebrate together the end of the semester. One more slot in the mystery game, one more chance to win. Thank you, Georges, for moderating, for organizing the mystery game with the TA team. Thank you, everybody, for attending. Enjoy the exercises, and I will see you next week for the final lecture.